start the recording. All right, so let's get started. Yeah, we're very happy to have a talk by Daniel Rade on scalar and mean curvature comparison for Romanian bands. All right, please begin.
Yeah, thank you for the introduction and thank you for the invitation to speak here. Very good pronunciation of the last name. Very good. So so I'm going to talk today about some work I did in my thesis, which I handed in 2 days ago. So it's pretty fresh, feels good. And now let's talk about it. So I'm very happy to talk here. I think I've given this talk in Germany, like all over, but nowadays, sort of everybody knows about it already. And this is like the first time in a while that I'm speaking to some people who maybe haven't seen it. So this new outreach. So this is based on my work, and some parts of it, which are then clearly marked, are also based on joint work with Rigidity Zeidler from Münster and Cecchini from Berkeley. So for anybody who was wondering, this is sort of my rendition of Gromov blowing soap bubbles. That's basically what this talk will be about in some regards. All right, so the title is Scalar and Mean Curvature Comparison for Riemannian Bands. So I'm going to explain what a band is. And the definition that I chose, and there are varying degrees of definitions out there, is the following. For me, a band is a connected and compact manifold, and it has a boundary, and you decompose this boundary into 2 parts, like a negative and positive part, and both del plus and del minus need to be non-empty. So your manifold needs to have at least 2 boundary components such that you can decompose them in this way. And just sort of for people who haven't seen it that much, let's draw some examples. So of course, you can only draw surfaces. So the standard one would be just a cylinder, but a band doesn't need to be a cylinder. You can have lots of topology, you can have lots of boundary components, and so the list goes on and on. So this is sort of the topological object. And then of course, since we're doing differential geometry, we choose a Riemannian metric on those bands. So if X is equipped with the Riemannian metric G, then the tuple is called a Riemannian band. And then sort of one invariant that we're very interested in is the width. And that is just the distance between del plus and del minus. So if you have a compact connected Riemannian manifold, you will find sort of a shortest geodesic connecting the left and right boundary components. And the length of that will be the width. Okay, and then sort of from our topological objects, we also have some morphisms. So we have bands, and then we have band maps. And the band map is nothing else than you have 2 bands and a continuous map between them. And that will be a band map if it maps, del minus to del minus and del plus to del plus. So I've drawn one example that sort of shows you that you don't need to stay in the same dimension all the time. Okay, you have a cylinder, you just project it down to the interval, and then you choose any path in another band from left to right, and that will also be a band map. So also these band maps are very flexible if you need them to be. All right, so maybe the first thing that one can see is if we talk about lower curvature bounds on bands and sort of try to figure out if there are any restrictions on them, is that on an open manifold, and therefore sort of on a manifold with boundary, there are no restrictions to existence of metrics with any lower curvature bounds. There's just, on an open manifold, there's an H principle of Gromov, and it just says any lower sectional curvature bound that you want, you can find a metric which has that. And then if you're a manifold with boundary, you sort of add a little bit of an open collar, find such a metric there, and then you restrict it. And then you find a metric with any lower scalar curvature bound on your band. So the question is, okay, this lower scalar curvature bound problem, which is very interesting in a closed case. In the case of boundary, maybe not immediately that interesting. So the question is, can we add boundary conditions for the metric and topological conditions on our manifold X to make things more interesting? So those are sort of the 2 ingredients that we're looking for. So X is our manifold, we add some topological conditions on X, and we add matrix conditions on G. Then we try to sort of find some restrictions and some sort of forces which pull in different directions, and from their interaction we can maybe find some nice results. So these boundary conditions in our talk will be phrased in terms of the mean curvature of the boundary. So just because there's lots of conventions out there, let's maybe say what I mean. So that's just a manifold boundary. And then I look at the interior unit normal vector field. And for me, the mean curvature is the trace of that. But that sort of is not enough to clear up all problems, because people have different conventions about second fundamental form as well. So let's just say the convention is such that if you have the unit ball in Rn and its boundary, which is the unit sphere, and you take the interior unit normal vector field, then with this condition, the mean curvature of that is n minus 1. Okay? So the boundary of the unit ball has positive mean curvature. All right, so then if we ask these questions, we sort of look in the literature and find immediately two results that point in the direction that there's something possible. And the first is a theorem, which is basically due to Gromov and Lawson, although there are some ingredients by other people, I guess, which I mentioned. And it's the following, okay? You take a band, you take a very easy one, a trivial band, it's just a cylinder. Take a torus and you cross it with the interval. And then you pick a Riemannian metric on X with scalar curvature, which is, okay, I can actually put this here, okay, bigger or equal than n times n minus 1. And then the infimum of the mean curvature of the boundary has to be smaller than 0, which sort of, if you phrase it the other way around, means that you cannot have a metric of positive scalar curvature on X, which has non-negative mean curvature. And the proof due to Gromov and Lawson goes by a doubling procedure. So the idea is the following. You sort of assume that you have such a metric, then you take two of them, and then you glue them together sort of along their isometric boundaries. And the problem is, sort of with this gluing, you will not get a smooth metric. So I try to draw a crease here. I don't know if it's very noticeable, but yes, yeah, it's not smooth. And what you then do is you smooth it out. And sort of there is this general principle, which is started by Gromov and Lawson, and then there was this guy Almeida, I think he's a student of Lawson's. And then more recently, there's work by Christian Baer and Bernhard Hanke, my advisor, which sort of gives you a way of smoothing this out. And you can smooth it out if the mean curvature is non-negative and the scalar curvature is strictly bigger than 0, yeah, which is sort of given here. And then you can smooth it and you only lose a little bit of scalar curvature. So if it was positive before, it will be positive again afterwards. But the double of this is just the n torus. Okay? And we know sort of this doesn't have a positive scalar curvature metric, so that is a contradiction. All right, so that is sort of the first boundary condition, sort of for positive scalar curvature, non-negative mean curvature seems to be a good boundary condition to get some restriction. And then sort of almost 40 years later, there's sort of this different trend in boundary conditions. And that is talking about the width. So I don't know if it makes sense. Sort of, I consider the width to be a boundary condition. Okay, it says something about how far boundary components are away. So there's this other theorem, which is sort of proven by Gromov first, in dimensions smaller or equal than 7. And then there is this index theoretic story by Cecchini and Zeidler. So they proved it in all dimensions. And again, you take the same manifold, torus cross interval, and then you pick a Riemannian metric on X. You pick again, I don't know why I was not able to write down the right curvature bounds. You take scalar curvature bigger or equal than that of the n sphere. And then the width, which is again this distance between the left and right boundary, is bounded from above by 2 pi over n. So sort of a very easy picture in 2 dimensions is sort of, if you want to have more curvature, you sort of push everything together and then in this picture, sort of this 2 pi n just comes from the fact that everything sort of, if you have positive curvature, everything closes up. And then the idea sort of in higher dimensions is that you can do the same thing because a torus doesn't have positive scalar curvature. So if the whole thing has positive scalar curvature, and you can't sort of put it in the fiber direction. The process curvature has to manifest itself into the direction of the interval, and therefore you have this closing up procedure. All right, so as I said, Gromov proved this using minimal surfaces with free boundary minimal surfaces, and did the usual induction descent method with some warping functions. And then Cecchini and Zeidler sort of completely separately developed an index theoretic approach to these questions. Okay, so they sort of added potentials to the Dirac operators and did some clever stuff, and they were able to prove this in all dimensions. And of course, sort of I only picked one example. So in the result of Gromov, as well as in the result of Cecchini and Zeidler, they don't just have it for the torus across the interval, they have it for more general things. And in particular, for Riemannian bands, which are not trivial. And you don't need to be in a cylinder for that. All right. So if there's no questions, let's continue. So
actually, let me ask a quick question if you go back for a second. So the lower bound n times n minus 1, that's so that when you double and then smooth, you need like a little bit of room to make sure it still has, okay, but it's kind of any lower bound on scalar curvature.
No, you can just write down scalar curvature bigger than 0. No, I just wanted to sort of always have the same lower scalar curvature bound everywhere, but you can just write bigger than 0. The theorem works the same way. Okay, so sort of the thing that motivated me to start thinking about this question is sort of an idea of Cecchini and Zeidler, and if you look really closely, you can find it in Gromov's 4 lectures, is that sort of these two theorems, although they look completely different, okay, the first one says something about a lower scalar curvature bound, and then you look at lower bounds of the mean curvature maybe, or upper bounds on the mean curvature, or its infimum. And the second theorem is you have a lower scalar curvature bound, then you have this upper bound on the distance between the two boundary components. And sort of a just general question that one can ask is sort of, is there a relation between the two? So does this one theorem sort of depend on the other in any way? And the answer that we will see in this talk, hopefully, if I get through all my slides, is that there is a general principle which governs both results. So we will see what we call a scalar and mean curvature comparison principle, and then sort of the first and the second theorem are just the extremal cases of that. All right, that's sort of the goal for this. And of course, we want to find the most general formulations of these theorems that are possible. So the most general topological conditions in X and the most general metric conditions. All right, so we have a tool. We have one good tool in our geometric part, and this is mu bubbles. So I just try to pack everything that you need to know about mu bubbles in one proposition. Okay, so we will not sort of go into the geometric measure theory. I just give you the box, the black box that you need for everything that comes. So the proposition goes as follows. So you have an oriented Riemannian band, and you sort of fix a dimension less or equal than 7 for sort of GMT purposes and regularity theory of minimal surfaces. And then on this oriented Riemannian band, you pick just a smooth function, and function x to r, which is going to be called our potential function. And then the proposition says the following. So if the mean curvature of the boundary, and here you should read like the plus goes with this plus and the minus goes with the minus, is sort of bigger than this potential function or it's negative on both ends, then you will find a closed embedded hypersurface sigma, which separates the left part and the right part of the boundary, which just means that any path which connects them has to intersect it. And the mean curvature of the sigma will be equal to the potential function restricted to sigma. Okay, this, if you write it down, comes from the first variation formula of this functional that you minimize to get this sigma. And then the second fundamental form, the second variation formula sort of gives you this inequality for an operator, for sort of the Laplace operator plus the scalar curvature of this sigma. All right, so how does this look like? Okay, we have some Riemannian band here, and then through GMT magic, you produce this thing here, the separating hypersurface. And what you see immediately is that it doesn't need to be connected. Okay, that's sort of the point I want to make with this picture. It doesn't need to be connected, can have multiple components, but the only thing we need is sort of every path from left to right has to cross one of those components. And this here, this is sort of a barrier condition. So if you try to find this using the write on a functional, you minimize it, then this sort of tells you that you can always push in a little bit from both boundary sides. So you actually find something smooth in the interior. All right, so this is the proposition. And then we sort of look at this operator. And if you've done any positive scalar curvature geometry, you know it well. And what you know in particular is that if this one is positive, strictly positive, then sigma will admit a PSC metric. Okay? So this is sort of the observation we make. So if we have this barrier condition, and if we have such a potential function, we find such a sigma, and then we sort of can guarantee that the right-hand side is strictly positive, then this will be bounded from below, uniformly from below by something positive. And then we know that this sigma, the separating hypersurface, all of its components basically will admit a metric with positive scalar curvature. And sort of you have to sort of distinguish two cases in dimension. If sigma is two-dimensional, then you use Gauss-Bonnet, and if sigma is higher dimensional, then you use this conformal change argument, which sort of was used by Shane and Yao, but goes back to the work of Karsten and Warner. All right, so from this, we form a strategy as to how to get nice results. So the first is we investigate conditions on the metric which guarantee the existence of such a smooth potential function, such that, okay, we have this boundary condition, and furthermore, sort of this ODE is fulfilled, right? Because then we know the sigma is PSC, and then we hope that sort of with this PSC on sigma, we can do something. And then the second point is we investigate topological conditions on the band, which sort of guarantee that this is not possible, which guarantee that no closed embedded hypersurface, which separates these two boundary components, admits a metric with positive scalar curvature. And those are sort of the two forces which push in opposite directions. So we can find metric conditions under which we will find a hypersurface which separates and which has PSC, but then the topology of X does not allow it, right? And this is sort of the two ingredients that we use. Are there any questions concerning this? Okay. All right. So I told you that we want to do a comparison theory, right? So this is something that, how do I say this? I think the idea for me to do this came from the work of Cecchini and Zeidler. I mean, we've seen it in the Gnostic seminar. There was this talk about scalar and mean curvature comparison via the Dirac operator, right? So I looked at this paper, I talked with the authors a lot, and I sort of, while reading the paper, tried to understand what they mean by scalar and mean curvature comparison, and sort of how this comparison theory that they were proposing fits in sort of the story of classical comparison geometry. So for me, comparison geometry looks like this. You have some arbitrary space, and then you have model spaces. Then you have sort of compare metric properties of this space you start with metric properties of the model space. And then sort of if you have good comparisons between these properties, you can say something about sort of the relation between the thing you started with and the model space. So since Simona and Rudi did not define model spaces, it was sort of implicit, I try to figure out sort of what a good notion of model space is, and then again, if you look at Gromov's papers, sort of deep in there, it's already written down. So for us, a model space will be a warp product. So let me just remind you sort of what warp products are. Okay, so we start with a closed manifold and with the metric Gn, and then you have some positive function. And then we always denote these warp products by mg phi. Okay, and this is just take n cross this interval, and then you sort of have this warp product metric. And there are some formulas sort of that are interesting that we need to know is, okay, the first thing is about the mean curvature of a slice. Okay, so NT will be just a slice in this product. And then I look at the mean curvature of NT with respect, again, to this interior unit normal vector field. And this will be just n-1 times phi prime divided by phi. Okay, so phi is always positive, so we can actually write this down. And then we will define sort of this to be a function h phi. Okay? So whenever you'll see an h phi later, it's always, okay, just this. We have a warping function phi, and h phi is sort of what we derive using this formula. All right, so here's a picture of a warp product. And the second formula is concerned with the scalar curvature of a warp product. Okay, so the scalar curvature of this thing at a point P and T is nothing else. Okay, so I didn't put this on one side, but what you get is you have the scalar curvature plus n divided by n-1 of this h phi plus 2 h phi prime, you will get sort of a function in the scalar curvature of ngm. Okay, cool. So at this point, we sort of see why these warp products appear as model spaces. If you look back at our toolbox, okay, so let's go back to the toolbox, okay, here. So this is what we're interested in, okay? We need to find a function h such that this is positive. So sort of in a warp product, if you have this h phi here, and then you have h phi prime, this will be equal to 0. So sort of warp products give you good functions h, which already sort of almost solve this ODE. Then you hope that you can sort of get positivity by wiggling a little. So sort of in the mu bubble variational formulas, sort of the scalar curvature formula for a warp product appears. Okay, and as I said you have equality if, okay, you choose a scalar flat manifold, and we're also going to do that. Okay, so ngn will be scalar flat, then we have a 0 here, and then the idea is sort of you can, if you start with a Riemannian band, construct suitable potential functions by pulling back h phi from a warp product, okay, such a mg phi over a scalar flat manifold, such that we have a 0 here. Okay. This will always be 0. And the only thing you need is sort of a band map from your thing to your warp product. Okay. So you need a band map from X to M. And then you sort of already almost have a comparison setup. You have a Riemannian band, you have a warp product, you choose a comparison map. And then from this comparison maps, you sort of pull back things to X. And if everything works nicely, you can then use this mu bubble toolbox to sort of produce results. All right, so you cannot just use any warp product. And the reason is sort of that here we have sort of the, we have H prime, but in the second variational formula, you have like, if you estimate from below minus the gradient of H. Okay, so if H prime is positive, sort of things don't fit together. So you need to find functions where sort of this H is already strictly decreasing. So H prime is negative, and then sort of the minus the absolute value of H prime is exactly the same as H prime, so that the formula fits. And okay, there's other reasons why we choose the strictly log concave functions, but let's maybe first say what they are. So a smooth function, which we use then as a warping function, is called strictly log concave if you sort of look at log phi, take the second derivative, and that is negative. Okay, so the first derivative of log phi is this phi prime over phi, which we already saw appear sort of in the definition of this H. And therefore, if you have a strictly log concave warping function, then what you sort of see is that H phi prime is negative. So this potential on the warp product is strictly decreasing. And then we actually define sort of what our model spaces are. And those are just, you take any closed scalar flat manifold MGN, and then a warp product mg phi over this space is called a model space if the scalar curvature of the whole thing is constant and this warping function phi is strictly log concave. Okay. So this is sort of a choice I'm making for model spaces. And
I can ask a question.
Yeah.
So does an annular region in like a hyperbolic space satisfy this property?
So it does not. So for this talk, I'm restricting myself to base manifolds which are scalar flat. So what you're talking about is basically a warp product over a sphere, right?
Yeah.
So I like in some of the versions of papers or theses I've written, the notion of model space is more general. And there you just sort of want that this NGN is a closed manifold with constant scalar curvature. And there's also comparison results from that for that, which we have seen sort of in the work of Cecchini and Zeidler. But for this talk, I restrict myself to closed scalar flat ends. So the annular region does not play a role here, unless of course you talk about the hyperbolic plane, right? Because then you have an S1, and that sort of has no scalar curvature, so that in 2 dimensions this would classify as a model space in this talk.
Okay, thanks.
Okay, so right, so now we want to set up sort of our comparison result. And sort of the last thing you need is, I told you that sorry for skipping around so much. I personally don't like it when other people do it, but giving a talk, you sort of find yourself making the same mistakes. So we sort of need this band map from X to M. And it turns out that you want this to be one Lipschitz. Okay, so you want this to be one Lipschitz such that if you sort of pull this back, this H phi, and look at the gradient of this function H that you get from the pulled back one, then if this is equal to 0, the pulled back one, if you look at this ODE, you will get bigger than 0. Okay? So you want this to be strictly one Lipschitz. And there is this lemma, which many people have proven now, and it's sort of very clear that if you have a Riemannian band and its width is bigger or equal than B minus A, then you will find a smooth band map from X to the interval, which just means the del minus gets mapped to A and the del plus gets mapped to B, such that, okay, this thing has Lipschitz constant strictly smaller than 1. So you basically just use the distance functions from the 2 boundaries, and then you get a 1 Lipschitz function, and then you sort of smooth it out a little bit. Okay, and then I already told you that we sort of split the problem in 2 parts. One is a metric part, find sort of conditions on G, and the other part is a topological part. And sort of to write down the most general metric result, I would sort of, for now, black box the topological part, which was that sort of on a band, no closed embedded hypersurface, which separates the 2 ends, should admit PSC, right? And I call bands which are like this just bands which have property A. It's just sort of a way of denoting this whole sentence, so that I don't have to write it all the time. And then there is the comparison result, okay? So that we set up. So you have n smaller or equal than 7. You have xn, an oriented band, which has this property A. Then you choose a Riemannian metric on it. And then you choose a model space. Okay? And then you say, all right, we compare our band with this model space in scalar curvature and mean curvature. And if the scalar and mean curvature are bounded, okay, and here, of course, you have plus to plus and minus to minus. If you have a lower bounds on the scalar and mean curvature, then you get an upper bound on the width. Okay? And that is the comparison of that. All right, so this is sort of the first main theorem in the paper, and sort of the goal that we had. And let's maybe, since we just set it up, let's maybe sketch just verbally how this is about to be proven. Okay, so I will not write down a proof. Let's just go through it. Sort of the notions I introduced should help us along. Okay, so we know we have scalar curvature is big or equal to the scalar curvature of this, mean curvature is big or equal to mean curvature of this, and then we assume for a contradiction that the width of x g is actually bigger or equal than the width of mg. Okay, but what is the width of mg? Okay, this is sort of just b minus a, right? So if you have this warp product, then it's like manifold cross interval, and you have a dt squared in the metric. So the width is just b minus a. And then first we use this lemma. Okay? This lemma here. We have assumed the width is bigger than b minus a. Then we will find such a smooth band map sort of from x to ab with Lipschitz constant smaller than 1. And then we sort of notice that since the width is strictly bigger, it's also strictly bigger than, let's maybe erase this, than b minus a plus 2 epsilon. Okay, you can sort of put a little epsilon in there, and then you will get a map to like a minus epsilon, b plus epsilon. And of course, sort of if you have this model space and the warping function is defined on AB, then in all of the cases we actually look at, sort of the warping function is also defined on this slightly bigger interval, right? And then we use this phi to pull back the h phi from the model space. Then we get a function on x, which we call h. And it turns out that this actually has all the properties we want. So we will have the strict barrier condition because we have this epsilon here, and we know that this h sort of on the right-hand side decreases and on the left-hand side increases. And that's sort of all we want for our mean curvature condition. So this epsilon guarantees that we have the strict barrier condition. And then with the strict barrier condition, we will find our mu bubble, our separating hypersurface. Then we look at its second variational formula. Then let's go back to the toolbox. Okay, it will look like this. And then sort of we just plug things in here. So this is bigger or equal than the scalar curvature of m g war phi, g phi. And this h here is nothing but h phi composed with this phi. Okay, so in particular, sort of h squared is the same as h phi squared at the image point. Okay? And this scalar curvature is constant. So this is -1 h phi squared. And then this condition that the function was strictly log concave, and the fact that this phi, because the differential of phi appears sort of in this nubla here, is smaller than 1, and this is negative, guarantees you that this is sort of, let's put it here. So this is strictly bigger than plus 2h phi prime. And this, because of the formula for warp product, was equal to 0. Okay, and then we have what we want. Sort of this sigma, so this operator, Laplace plus scalar curvature, is bigger than 0. And then again, we observe that this sigma then has positive scalar curvature. But here we go back to the theorem. So we assume that this is impossible just because this band has this property A, right? This is sort of our a priori assumption that this can happen. All right. So in a way, it's a nice. I think it's nice. It's a very general theorem, and then to apply it, you sort of have to actually do some work. Okay. So you can apply it in two different directions. So A, you have to write down model spaces. Okay? So sort of for every model space that you can write down, you sort of get specific values for your comparison theorem. And then on the other hand, you actually have to find bands with property A. So if there are none, then sort of this whole exercise is worthless. So let's just start with the metric part first. So let's look at some model spaces. Okay. So we look at warp products. So Gn will always be a scalar flat manifold. I don't care what n is, what the topology of n is, just scalar flat manifold. I just care for the warping function, basically. So
wait, sorry, before we get too far into this, does this come with a rigidity statement?
Okay. So I think I have some rigidity slides.
Okay, it's later.
No, it's fine. It perfectly fits here. Okay, so there's a rigidity question here. Okay, so the question is, we have this. Okay, the theorem again is if those two things are fulfilled, then the width of xg is less or equal than the width of mg. And then the question is, what happens in the extremal case if the width is actually the same thing? And the conjecture, and I will put a lot of money on this one, is that if you actually are in the extremal case, then your band is isometric to a warp product. Y cross, okay, to a warp product with exactly the same warping function as your model space, and YGY has to be closed Ricci flat. And so in particular, if you're in the extremal case, your band has to be a model space, and it has to be sort of a cylinder, a trivial thing. All right, so we know this already in some situations. In particular, we know this if x is spin and the AH genus of del minus x is not zero. Okay, so that is sort of one category of bands with this property A. And for those using the index theoretic methods of Cecchini and Zeidler, you can prove this rigidity statement. So in the mu bubble approach, there are some hurdles that you need to overcome before you can prove this. Okay? And I mean, I told you sort of before we started the talk that I'm not the most well versed in GMT, so maybe these hurdles are not so big as I make them. But the idea is the following: what you would want to do is, under these conditions, you want to start off the same way. You sort of want to find a nice potential function, which you can still do. You can still pull it back. But the first problem you see is that this function phi that you use to go from x to m, which had Lipschitz constant strictly less than 1 before, may not be smooth anymore because you don't have space to smooth it. Okay, if you just go sort of from x to ab, you can do this. You get a 1 Lipschitz function, but it might not be smooth anymore. Okay, but let's say you can get around this. You can still set up your mu bubble functional. And then you are in the second problem, is that you don't have a strict boundary condition anymore. So as I said before, for the strict barrier condition, you had these epsilons. Okay, you can sort of push a little bit out, and you know that the mean curvature sort of behaves appropriately, and you can make the strict barrier condition happen. In this case, you cannot. So the only way to sort of guarantee that you still find a minimizer and it will still be smooth is if you can prove what in GMT is always called a strong maximum principle for this function, right? You sort of want to say that, okay, so you can find this minimizer, and then if it touches the boundary, it sort of needs to agree with the boundary component. And then if it's in the interior, you're good anyway. The regularity theory works. And that is sort of the second obstacle. And once you've overcome this, and you are in a situation where you actually have this smooth mu bubble, then you're good. Okay. At this point, you can use sort of the standard foliation argument that many people have used now, which sort of tells you that you look at this variation formulas for this thing, you know, it can't have positive scalar curvature. So then in the second variation formula, lots of terms have to vanish. And you actually see that sort of a neighborhood of this splits isometrically as exactly such a warp product. And then you just have to argue that sort of by geodesically flowing in both directions, you flow out the whole band and you actually get isometries there. So this is sort of based on this argument by Bray, Brendle, Nevish, I think, 2010, and it's also used in Anderson, Kay, Galloway. We have seen it in the work of Ju. So this foliation stuff works. You just need to find a mu bubble. So at this point, let's maybe go back to the theorem. Where is it? Yeah. So in my paper, I actually did some rigidity stuff. Okay. So here for my model spaces, I use strictly log concave warping functions, but there's another class of warping functions that is good, and I call them log constant, and that just means that the second derivative has to be equal to zero. And that just means that this h phi is constant. Okay, and if this h phi is constant, then what you sort of see is the width doesn't play a role anymore. So then in the theorem, what you get is if you have a model space with a log constant warping function, you have these inequalities for mean curvature, then you actually get a rigidity statement and see that this is sort of, it's a product manifold, a warp product manifold with exactly this log constant warping function. Okay, and this works just because you don't have to worry about this smooth Lipschitz function because the width doesn't play a role, because the model space is, for example, just a product, torus cross interval. So if you can make this as big as you want, you don't change, it's scaling invariant. You don't change the mean curvature or the scalar curvature. So you can just take any smooth function. So the first hurdle is overcome. And then for the second hurdle, you actually can use strong maximum principles that are in the literature. So if sort of this h is 0, then you just look for a minimal surface and your boundary condition is bigger or equal than 0. And you know that sort of there is strong maximum principles in these cases. And that also works if just h is constant. Okay, so because then you look for CMC surfaces and they have good maximum principles, basically. All right. Much ado about something. So let's do the application part. Let's look at warp products. The first one that we try to look at is, okay, we have this L minus and L plus, sort of from minus pi m to pi over n. And you take this cosine function with the appropriate sort of scaling in the exponent that you need. And then the warp product over some closed scalar flat manifold is a model space with scalar curvature equal to the scalar curvature of the n sphere. So if we're in a two-dimensional case and n is just sort of a round circle, then we actually just get S2. Okay? S2 without sort of the west and the east point is exactly such a warp product. And what you see is that this h phi is given by n minus 1 times the tangent function, right? And then we look at sort of our theorem. So the mean curvature of this left, maybe I should explain this. The mean curvature of this left-hand part is given by the blue thing, and the mean curvature of the right-hand side is given by the green thing. All right. So in this mu bubble thing, I had this del plus minus is bigger or equal than plus minus h. The reason for that is that if I look at the mean curvature of a slice, I evaluate it with the vector field in this direction. But once I get to the boundary mean curvature is evaluated with the vector field in a different direction. So if sort of this nt comes closer and closer, its mean curvature will go to minus the mean curvature of the left boundary that we actually want. Okay. So what we then look at is sort of these two curves. And then to use the theorem, we realize that we can always make this condition happen, right? So if you have a Riemannian band with a lower scalar curvature bound by n times n minus 1, then we can always find model spaces such that this is fulfilled just by sort of going out further, because on both ends, this mean curvature goes to minus infinity. Okay, so we can always sort of undershoot the mean curvature of X by going far out, right? So this is the thing we see. And then the corollary is just sort of the bandwidth estimate. Okay, so you have X-oriented band with property A, and then if G is a Riemannian matrix X with scalar curvature bigger or equal than n minus 1, then we can find the model space by sort of choosing L minus and L plus appropriately. And then the observation is that the width is bigger, less or equal than L plus minus L minus. And this is actually strictly, okay? So in the theorem before we had non-strict inequality, it's actually strictly less than 2 pi over n. Okay? And that's what I said is this bandwidth inequality is sort of one extremal case of this comparison principle, and extremal in the sense that sort of go with L minus and L plus to sort of the absolute limits you can push it to until this model space collapses, until the boundary sort of collapses to points. All right, but then also the other theorem, this theorem that was proved with the doubling techniques, can also be proved in this way. Okay, so if you have an oriented band with property A, you have a metric with this lower scalar curvature bound, then actually this infimum has to hold. Okay? And how does this work? Well, assume that, assume for a contradiction that the mean curvature is non-negative. Then we look at our graphs, and what we can sort of do is we choose our L minus to be 0, okay? And the L plus we can choose arbitrarily small, and still sort of, if you look at this model space, this will be fulfilled because the left-hand side is bigger than 0. And if we put this arbitrarily small, it will still be negative, right? So what we can do is we can do this comparison sort of with arbitrarily slim model spaces. And this sort of is a contradiction because the width of the band is some positive number. Okay? It's some manifold, the boundary has some distance, but you can do this comparison argument with arbitrarily slim model spaces. So somehow this theorem then gives you a contradiction because you undershoot this width estimate. Okay, so this is sort of the two ways that these theorems that we started out with are just extremal cases sort of this comparison principle. All right, so this one model space. It already gives us the two theorems that we want, but sort of there's lots more log concave functions to look at, right? So let's choose a different model space. You have this L minus and L plus. It's bigger than 0, smaller than infinity. And the warping function is just t squared, or t basically. And then you look at this warp product. And again, if you say n is just a circle, then you just get R2 without the origin. It is a flat metric. And this sort of is how you can write R2 without 0. Okay. Just you have this S1 and you have this warp product metric, right? But it works for any scale flat manifold if you sort of add this 2 over n function. And again, here, let's maybe also look at this. Okay. Again, this mean curvature goes with the blue curve. The other mean curvature goes with the green curve. And then the result is the following. You also have a width estimate, but you need stronger assumptions. So the theorem is oriented band with property A has non-negative scalar curvature, but the mean curvature on one side, and I choose the right-hand side, is positive. Okay? And then I say that then the width is bounded sort of by the infimum, by some function in the infimum of the scalar curvature. And the reason is sort of if, again, sort of the mean curvature of del plus, we look up on this graph, if it is positive, then I can find some L plus here, okay, such that this value of this function at L plus is this mean curvature. And then I realized that on the left-hand side, I go to minus infinity again. So on the left-hand side, I can again always undershoot the mean curvature at del minus, right? This I can do. And I sort of assumed that I can undershoot the mean curvature on the right-hand side. And this is this assumption on H plus. And then what I know is that the distance is bounded just sort of by the length of this interval. So the distance is bounded by L plus. And then sort of you just have to sort of calculate. You calculate this, and you have this H phi, and then this should be L plus. And then you put it on the other side, and what you get is sort of the width is bounded from above by this one. All right, so you get another width estimate, but you don't need positive scalar curvature. You just need non-negative scalar curvature and some positive mean curvature. And you can push this even farther and actually get results for lower bounds on scalar curvature, which are negative. Okay, there's also good model spaces for that. And what you see is that sort of you get a similar theorem where you have scalar curvature bigger or equal than minus n times n minus 1. But then the mean curvature has to be bigger than n minus 1. Okay? Because sort of this warping function that you get in this case, it looks like this. It's like cotangents, the hyperbolic cotangents, and that sort of goes to n minus 1. So you have to undershoot it by assuming that you have bigger or equal than n minus 1. But then this goes to infinity, it's negative, goes to minus infinity. You can again undershoot on the left-hand side. All right.
Can you, so sorry, this is, I'm trying to understand this. What is the, can you give me like a model space? Like what are some examples of these things?
For the
you said in
hyperbolic
dimension
one,
2, you get the flat, the flat R2 is an example. What's like a 3-dimensional?
I don't know, you take a flat 2 torus and do the same warping function. I'm not saying that, so if the model spaces, I'm not saying they always appear as annuli in some space form. I'm just saying you take a flat manifold and warp appropriately, basically.
Okay, so like a 2 torus warped like this, and then that will be some scalar flat non-compact thing.
No, I mean you always just go from L plus to L, from L minus to L plus with this warping, right? Mm-hmm. But then you mean sort of if you push it to infinity, yeah, then you get sort of what you get here with just deleting the 0.
Mm-hmm. And then could you go to the next slide? So this is a pretty general statement about any band which has, for instance, a toroidal class where the boundary is like a torus, for instance.
I don't know. So we will talk about this property A in a second, but it's not enough that the boundary is a torus for a band to have property A.
Sure. Okay. Yeah. But it's interesting because this is this seems very general.
It is very general.
Yeah, that's interesting.
Okay, so maybe that's something sort of this log concave stuff. You can all find it in the work of Rade and Simone, but sort of I looked at Gromov stuff and then he writes down some log concave functions. And so if you actually do all this and write it out, you see that. So if you can get width estimates and with other lower curvature bounds, just don't have this property that the mean curvature doesn't matter anymore, because you don't go to minus infinity sort of on 2 sides of the interval, but just one of them. Okay, so rigidity. Yeah, we talked about this. Okay, again, you would want to have it, and then sort of before we talk about this topological part, we talk about how you can push this even further, this comparison business. So this is now work with Rade and Simone. Okay, let me write this down. So this is joined. Okay, it's already written there in the theorem. So what we did right now is we took one band and we compared it to one warp product. And that gets you ever so far, but it does not get you to some theorems that you want. Okay, so there's this conjecture of Rosenberg and Stolz, which says that if you have a manifold which doesn't have PSE and it's not 4-dimensional, then if you take the product of this with the real line, then this thing doesn't have a complete metric of positive scalar curvature. Okay, so this bandwidth estimate before tells you that it doesn't have a complete metric with uniformly positive scalar curvature, because if you had that, then you could sort of pick some two slices, look at the band between them, and you have a bandwidth estimate which you can sort of overshoot by going farther off. But with this just positive scalar curvature on a non-compact manifold, you could sort of decrease once you go out, and you cannot use this bandwidth estimate with just a uniform lower bound. So to attack this problem, you sort of need to be a little bit cleverer. And what we did is we sort of tried to just use the things we had and glue them together. And this is this partition comparison theorem. Okay, so the statement is very long, and I don't even want to give a definition of what a partition band is. But let's just look at this picture. Okay, you have a band, and then what you do is you pick some separating hypersurfaces. Okay, those are these sigmas. Just pick them, and then those subdivide your band into smaller bands. Okay, into these segments. And then what you do is you have this, and for each of these segments, you compare the segment to a model space, sort of in the way we did it before. Okay, and these model spaces you can sort of glue together. So Simone calls this Frankenstein's model space. So you have all of these segments, and sort of the mean curvature sort of agrees at the boundary, but you cannot glue them together smoothly, but you can glue them together. And then what you do is you may have very different scalar curvatures on these model spaces, and then you compare sort of a partitioned Riemannian band, and each segment you compare to some model space, but sort of the scalar curvature of these model spaces can jump, and that's what you want to do. And then what this theorem tells you is that if this Vj are the segments, and these Mj are the corresponding model spaces, and then the same thing sort of you need is that the scalar curvature is bounded from below on all of these segments by their corresponding model spaces. Then you need on the left-hand side and on the right-hand side, so for the first model space and the last model space, you need this mean curvature barrier condition. And then you need that sort of the mean curvature is at least continuous when you go from one model space to the next one. So again, we have this minus because of our sign convention, but that just means sort of the mean curvature function is continuous if you pull it back. And then what you do is sort of for each of these segments, you define these functions phi. Okay. All right, so sorry, that was one sentence too fast. So if you have all of this, then the width of at least one segment is bounded by that of the model space. So it seems like rather a weak conclusion, but it just tells you that in this situation, not all of the segments can be longer than the model space that you compare them to. At one instance, you have an upper bound. Okay, so you get an upper bound on the width of one of these segments. All right, so how do you prove this? Well, you assume for a contradiction that on all of these segments, they are longer than what we compare them to. And then we do exactly what we did before. You use this lemma, which gives you these functions phi, and you have epsilons everywhere. Okay, and then if you pull back all of these functions and just glue them together, you get a continuous function. And you get a continuous functions because sort of this h phi is sort of the mean curvature of these slices. And then the second condition in the theorem means they agree. And then you use all of these epsilons that you had to get strict barrier conditions on the left-hand side and on the right-hand side, and smooth out the crease in your potential at all of these sort of not jumping points, but points where it's not smooth, right? So you use all of these epsilons, and then you use the same mu bubble procedure, okay? You have a potential, you have strict barrier, you find the mu bubble which separates, it will have PSC, can't happen as property A. All right, so this is this partitioned comparison principle. And then you just sort of see what you have done. So you look at an application. And the application is that we're interested in is we look at a band which is divided into 3 segments. So you have sort of a middle segment, and then you have a left and a right segment. And the statement is the following: if the scalar curvature of the middle segment is positive, so you can find some kappa such that you have this lower bound, and the scalar curvature of the whole thing is non-negative. Okay, so in particular on the left-hand side and on the right-hand side, you have non-negative scalar curvature. Then actually the width of this left-hand side and the right-hand side is bounded from above in terms of this kappa and the width of the middle segment. Okay, and what we do is in the potential world, we use this positivity that we have sort of in maybe a very small region of some sort of slice to, in our potential, go from plus to minus. Okay, we cross 0 using the tangents function. And once we've done that, we know that sort of we don't need positive scalar curvature anymore. Non-negative scalar curvature, as we have seen, sort of where was this? As we've seen here, okay, non-negative scalar curvature suffices to sort of blow up the potential. And then we do exactly that. We use sort of 1 over x as a potential, right? And what this looks like in sort of the 2-dimensional world is if you have a Watt product over S1 and you have some slice in the neighborhood of which where the curvature is positive, okay, then you sort of get this positive curvature, you warp. And then at some point, you know that the scalar curvature is still non-negative. But what happens is you just go with straight lines here. But since you have this positivity, this will collapse. Okay, so you cannot go infinitely far out without this collapsing, because to sort of get rid of this positive curvature, you would have to introduce negative curvature. You would have to do something like this. So get back to something which goes arbitrarily far. But you can't have this because sort of the scalar curvature is always at least non-negative. Okay, so we have the statement, we have this positive curvature somewhere, and then non-negative scalar curvature somewhere else. And this is enough to sort of guarantee that there is an estimate on the width of these 2 components. Okay, so I will use 5 more minutes. I'm sorry, I'm going a bit over time, but I want to say what this property A is. Okay, so we have a lot of nice statements for bands of property A. And now we need to actually say that there are some. So this theorem of Gromov and Cecchini and Zeidler suggests that torus cross interval has this property. Okay, and in fact, this is true. And what we see is that many more bands have property A. And I sort of chose a statement which looks good, a very general statement which looks good. And that's just that if n minus 1 is not 4, and y is a manifold of dimension n minus 1, it's closed orientable, and it does not admit a PSC metric, then in fact, the cylinder has this property A. Okay? So you can take any non-PSC metric manifold that you want. You take the cylinder. This dimension 4 is because in dimension 4, there's actually counterexamples to all of these width estimates and stuff. Okay, there's manifolds which are weird and they have no PSC because of Seiberg-Witten obstructions, and they sort of don't agree with this calculus, right? But this is property A, and how do you prove this? Well, you look at, you don't need a metric here, it's just a topological statement. You look at a separating hypersurface. It turns out that in this instance, you only need 1 component to separate, will be the sigma 0. And then you look at the cobordism between del minus and sigma 0, which is given sort of, which is just bounded by sigma 0 and del minus. And then you know sigma 0 has PSC, and there are these very general statements as to what happens if you have a bordism and the right-hand side has PSC. And what you need to see that the left-hand side also has PSC, which will give you a contradiction. And what you need to ensure is that you change this bordism by surgery in a way that makes the inclusion from the left-hand side to connect. Okay? And then it's just a general theorem. If you have a bordism, the left-hand side includes 2 connected, the right-hand side has PSC, then you can transport this PSC metric to the left-hand side, okay? But Y doesn't have PSC, so it's not possible. So this argument, if you want to prove it, is basically you start like this, look at this bordism, and you use the fact that you have a projection map to do this surgery to see that PSC from here goes to here. All right. And then we sort of put everything together. Okay, we have bandwidth property A, we have metric statements. So we sort of solve this bandwidth conjecture of Gromov in dimension less or equal to 7. And that's just, the bandwidth conjecture was just the torus statement holds for any manifold which is non-PSC unless its dimension is 4. Okay, so this is the statement. And then we also, using this partition comparison principle, solve this Rosenberg Stolz conjecture with Rudi and Simone. And we actually do more than this. Okay, so we would give very general topological conditions on a manifold such that some covering of it will be such a band where you can use this partition comparison principle. And a special case of this is exactly this. Okay, Y doesn't have PSC, it's not 4-dimensional. And then if you actually have non-negative scalar curvature on Y cross R, then you use Gromov splitting theorem to see that you actually get a flat thing. So this has no positive scalar curvature. All right, so sorry for going over time, but this is everything. Thank you.
All right, thank you. Let's thank Daniel. All right. All right, so we have a second talk. Very interested and happy to have Renato Bettiol here to tell us about extremality and rigidity for scalar curvature in dimension 4. So please begin. Thank you.
Well, thank you. Thank you for the invitation. It's a pleasure to speak in this seminar. So everything that I'll talk about is joint work with Jackson Goodman, who I believe was able to join us despite the very early time in his local time zone. So let's see. So I want to begin with a Riemannian geometry exercise that you could do in a first kind of class after you see Gauss-Bonnet, just to kind of motivate these notions of extremality and rigidity with very familiar objects. So let's imagine we pose the following question. So suppose we take a metric on the 2 sphere, and it's just some metric with non-negative Gauss curvature. So suppose this guy has Gauss curvature bigger or equal than 0, and it doesn't have to be the round metric, anything, right? And we want to know whether we can increase this Gauss curvature without shrinking any areas. So the question is, can you increase the Gauss curvature of this 2 sphere without shrinking any areas? Because if you're allowed to shrink some areas, it's pretty clear what you do. You just make it smaller, and then the curvature will go up, right? So you're not allowed to do that. So let's see. Let's imagine. Let's pretend you can, right? Let's imagine that you have some metric G prime which does just that. So let's suppose you have some G prime, and the Gauss curvature of G prime, I'll call it K prime, is bigger or equal than the original Gauss curvature. And no areas got smaller. So if I look at the area element, dA prime, that's bigger or equal than dA. Okay, so let's imagine we have such a thing. Well, then by Gauss-Bonnet, we know that the total curvatures are the same, of course. So if I integrate K prime, dA prime, I better get the same thing as if I integrate K dA. That's for pi, of course. And we can also use another big hammer here, which is the uniformization theorem. And by the uniformization theorem, we know that every metric, G and G prime in particular, they're all conformal to the round metric. So both G and G prime are in the same conformal class. They're both conformal to the canonical metric with constant curvature. And up to changing coordinates, so there should be a diffeomorphism here that I'll just pretend is the identity, just to make things a little bit easier to write. But up to changing coordinates, we can assume that they are conformal. They are just, there's a function multiplying one to get the other. So let's say G prime is e to the 2u times G for some function u on the sphere, right? Well, in this case, the area, the element of area is easy to write. If I multiply by a function, this would be the function raised to the dimension n over 2, which is 1 in this case, n over 2 is 1. So I get just e to the 2u times the area, the element of area of G. And we assume that this is bigger or equal than dA. So from this, I know that e to the 2u is bigger or equal than 1. With this, I can compare these two integrals with the same measure. So if I put both on the same side, I get k prime times e to the 2u minus k integrated with respect to the original area element. This should be equal to 0, right? I just replace dA prime with e to the 2u dA and move it to the other side. I get this inequality. And e to the 2u is bigger or equal than 1. So this whole thing is bigger or equal than just the integral of k prime minus k, which I assumed was non-negative, right? K prime minus k is bigger or equal than 0. I'm assuming that it's larger. But this integrates to something that is less or equal than 0, so it better be 0 everywhere, right? So you conclude from here that k prime is actually equal to k everywhere. So there's no way to improve the Gauss curvature if you're not shrinking some areas, right? And this is called extremality. So we'll call this situation here extremal. So this is what we mean by area extremality. This is usually what's meant by area extremality. And of course, in dimension 2, scalar curvature is just Gauss curvature. So we're just looking at that. There's something else you can do if the manifold has strictly positive curvature. So let's suppose that here, instead of just bigger or equal than 0, I put strictly bigger than 0. Then we can actually push this a little bit further because, well, then I could stop at this part. I still have the inequality, right? This here is also bigger or equal than 0, since e to the 2u is bigger or equal than 1. So I conclude that k prime e to the 2u is equal to k. And I already know that k is equal to k prime, right? From what we did before. But now the fact that this is positive means that I can divide by it everywhere, right? So I can actually divide by k prime everywhere. And I end up getting that e to the 2u has to be equal to 1 everywhere, which means that the metrics are actually the same since they were related like that, right? So there's a stronger notion of rigidity that comes out here, right? So this is what we call area rigidity. So in one case, the curvatures must agree. In the other case, the stronger conclusion that the metrics agree can be obtained. Okay, so that's a very satisfactory picture in dimension 2, at least. You can do something similar for negative curvature too, which is kind of cool. If you have any surface, the same kind of argument that we just described means that any surface whose Gauss curvature doesn't change sign, the only way to increase it in absolute value is to shrink the surface. So if it's negative, you can't make it more negative unless you shrink something. Right? So the same proof sort of gives you that. And then these notions, of course, they generalize to higher dimensions. So let me write here what I mean by. Actually, before I do that, let me do one last observation, which is useful for later, before I forget, which is, what if I have a two-sphere with non-negative curvature, but not positive everywhere? So you could ask, this extra conclusion that I got, right? This stronger result, does it hold also here, even though I can't divide by that? And the answer is actually easy to build examples that show it does not hold. You can't hope for this stronger conclusion. You can do the following. You can just take a little cylinder and cap it off, right, with no negative curvature. So if this region here has zero Gauss curvature, then you can just make it larger, right? You can kind of make the cylinder piece larger. You just change the element of area. The curvature is the same, but you're just building up some more area in there. And these are of course counterexamples to it, right? I mean, the metrics are not the same, and yet they satisfy the inequalities in the right way. So if you just have non-negative sectional curvature, but not, or non-negative Gauss curvature, but not strictly positive, you don't get this this stronger conclusion. Okay, even in the case of surfaces. All right, but as I was saying, there wouldn't be much to talk about if we're just doing dimension 2. So let's just state definitions that generalize these 20 dimensions. So I'll say that a closed manifold, a closed Riemannian manifold, MG is area-extremal for scalar curvature, which I'll omit, if the same business holds here. So if any G prime that has scalar curvature bigger or equal than, maybe I'll just write scalar prime bigger or equal than scalar G, the original guy, and elements of areas along all surfaces bigger than or equal to the original elements of area. So the way to write that is wedge 2G prime bigger or equal than wedge 2G. So this, in some sense, this means that dA prime is bigger or equal than dA along all surfaces inside our manifold. Okay, so for all two-dimensional surfaces inside them. Then, under those conditions, equality must hold in this inequality here. So then scalar curvature prime is actually equal to scalar curvature. Right, so that's the way to generalize this notion of area extremality. And we'll say that it's area rigid. Maybe I'll try to keep that in red. So the stronger notion of rigidity, if you get that G prime is actually equal to G, if the metric tensors are the same under the same assumptions, right? So if the same set of inequalities implies that the metrics actually agree. Okay. Okay. So these notions appear in several works. Notably gained a lot of traction recently with several works of Gromov. But the first, I guess, result motivating all this goes back to LaRue. So just remind us here, this is back in '98, that the round sphere is area rigid in all dimensions. So you do get this strongest possible notion of rigidity, that you cannot increase the scalar curvature without shrinking areas somewhere, not only in dimension 2, but actually in any dimension, right? So that's a very beautiful result that then got pushed to somewhat more general spaces by Goethe and Semmelmann. So there's a couple works in 2001, 2002 of Goethe Semmelmann, building on some works of Minou. And the main assertion that I want to make here is that if the Euler characteristic is non-zero and the curvature operator is positive semi-definite, then the manifold is area-extremal. So then M is area-extremal. Of course, you'll note that this is a very strong curvature assumption. It basically means, well, if you evolve it by Ricci flow, you know that the universal cover splits as a product of either spheres or Euclidean space or something by holomorphic CPN or some symmetric space, right? So they're very, very special manifolds. And there's a companion results to this in the Kähler world. So if the manifold is scalar and has non-negative Ricci curvature, then you also get the same conclusion. So the manifold there is also area-extremal. And both of these can be promoted to results about rigidity. So if we want the stronger conclusion that the metric tensors are the same, here you can bump this up to strict inequality, or you can also put some pinching assumption. So something that looks like this: scalar curvature over 2 times the metric is bigger than Ricci, bigger than 0. So under those assumptions, you get area rigidity. In the Kähler case, you just need strictly positive Ricci curvature, then you get area rigidity. So in both of these cases, you can promote area-extremality to area rigidity by adding this extra stuff in red in each of the two. So these are two separate results, of course. Maybe put 2 dots here. The conclusions are the same, but the sets of hypotheses are different. Okay. And as you see, all these either have some assumption on the holonomy, right? You have special holonomy. Here, you're basically symmetric spaces as well. So the class of manifolds, in addition to spheres, of course, is not too large. And Gromov notes this and asks for criteria to prove these kinds of conclusions in perhaps slightly more general classes of manifolds. So as Daniel was mentioning in the talk right before, dimension 4 is very weird for many reasons. It also makes it a good testing ground to try to do these things where sometimes slightly weaker looking curvature assumptions might be stronger than they reveal themselves at first. So that's what I want to focus on. So in dimension 4, we can try to prove extremality results with somewhat weaker assumptions than say these. Okay. So the main driving force behind this, the reason why we can weaken these curvature assumptions, is something that is generally accredited to Thorpe. It's usually called Thorpe's trick. Turns out that this very same result actually follows from a much earlier observation due to Finsler in a slightly different context. So I've been trying to push for this to rename it the Finsler Thorpe trick. And it states the following. So if you have a 4 manifold, I'm stating it in this very special situation. It's a slightly more general result for, I mean, it's a result in real algebraic geometry, if you wish, but in the case of 4 manifolds and sectional curvature, it states that a 4 manifold has non-negative sectional curvature, which I'll write like this, if and only if something happens with its curvature operator. So if and only if there exists a function tau, real valued function on the manifold, such that when I look at the curvature operator and I add to it tau times the Hodge star operator. So remember here, curvature operator acts on 2 forms, or 2 vectors, bivectors. In dimension 4, so does Hodge star, right? So Hodge star also acts between these 2 spaces. So if I take a linear combination of them, I can put this function tau in front of Hodge star. I add them, I have another operator. It's also symmetric from wedge 2 to wedge 2. This guy needs to be positive semi-definite. If that's positive semi-definite, you have non-negative sectional curvature, and vice versa. If you have non-negative sectional curvature, such a tau exists. You could also promote this to strict positivity here and there. The statement carries over exactly in the same way. So you can do positive semi-definite or strictly positive definite, and that corresponds to non-negative sectional curvature or strictly positive sectional curvature. Okay. And then, so this makes it very tantalizing to say, well, you were able to prove extremality, right? Go to Semmelmann, have this extremality result under the assumption that the full curvature operator is positive semi-definite. Maybe if you have this kind of perturbation of it being positive semi-definite, you can still get something. And that's exactly what we do. So let me state the first main result. And I guess I should have mentioned this a while back, but of course, if you have any questions at any time along the way, should stop and yell at me or something.
Well, I was going to ask,
yeah.
So what is the function? is it a Q? I forget. What is the, how do you
Oh,
construct that?
this is a very ugly looking tau. It was an attempt at drawing a tau. Yeah, but
And so how do you, can you describe that?
yes and no. So typically it's not unique. So if you have strictly positive curvature, say you take the force sphere with a round metric, right? Then the curvature operator is just the identity. Hodge star has eigenvalues plus and minus 1. So in a convenient basis, this is a block, a 3x3 block, identity minus identity. And so in this case, if I do R plus tau Hodge star, this is positive as long as tau is less than 1, right? So anything that, any function whose values at every point is less than 1 will be fine. But then, of course, here you're saying, well, I have strictly positive sectional curvature, right? So you have a lot of wiggle room. Indeed, the interesting case is when you have some flat planes. So if you replace this metric, maybe you put a different metric on the force sphere that has some flat planes. So some regions where at least one plane is flat. I don't need all of them to be flat, but at least one plane is flat. That nails down the value of tau to only one possibility. If it exists, it's just one point. There's just one value. So that makes it a lot more interesting. So for example, if you take S2 cross S2 with the product metric of round metrics on the two sphere, the curvature operator here has a bunch of zeros. It looks something like 1, 0, 0, 1, 0, 0 on a convenient basis. Hodge star is going to have some pluses and minus ones all over the place. And there's nothing you can do with it. If you add any multiple of Hodge star to this operator, it's not going to be positive semi-definite unless tau is identically 0. So in this case, it has to be that 0. There's nothing you add. The operator is already positive semi-definite, and you can't fiddle with it at all. Like, it has to stay that way because you have flat planes at all points, right? So the function tau is unique. So to answer your question more succinctly, perhaps, if you have flat planes, wherever you have flat planes, the value of tau is unique. What it means is a bit of a mystery for me still. If you have no flat planes, everything's strictly positive, then the set of taus that make this work is an interval because it's concave, right? It's convex. It's this condition here is convex, so it ends up being an interval that generates a single point when the curvature is 0. Is that more or less? I mean, I know it's not very illuminating, I guess, but at least you have some examples.
Yeah, is there so okay, the non-negative sectional curvature, I thought was, my thinking is it's a significantly weaker than non-negative curvature operator. So is there an example like where the sectional curvature is non-negative, but the curvature operator isn't non-negative, but you can find a tau that makes this work out? Or
sorry, so if the sectional curvature is non-negative, yeah. So CP2 connected some CP2 bar.
Okay.
So on this manifold here, you have non-negative sectional curvature. The curvature operator is not positive semi-definite because if it was, this would be a symmetric space, and it's not. So the function actually, not only the sectional curvature is non-negative, there are 0 planes everywhere on the metrics that we know. We don't know any metrics where the curvature is strictly positive at any open set. And so the function is determined. There's just one possible value of it at all points. And depending on how you draw this thing, I mean, let's imagine you draw it as a line, which is a terrible way to draw it, but you can imagine you have CP1s inside this. This is gluing 2 disk bundles over CP1. So these are the CP1s. Then the function has to do something like this. It changes sign in the middle of the place. I can, later on, I can give you a better description of what this picture really means, but the function is uniquely determined there.
Okay, yeah, that's helpful. I just wanted to be, my thinking is that the tau saves you somehow, and I guess this is a situation where it's important to have it. Yeah. Yeah.
In this case, yeah, there's only this tau, and that's the only way you get R plus tau Hodge star positive semi-definite. There's no other way. Yeah.
Okay, thanks. That's helpful.
Sure. While I'm at it, you could also do CP2 connected some CP2 without changing the orientation. And then this tau will look something like this. You just kind of reflect one of the sides up. And that will be very important in just a minute. Well, actually, right now. So when I state the theorem, you'll see that I'll need some sign condition on tau. Okay. So anyways, just to recap, we have this Finsler Thorpe trick. It characterizes non-negative sectional curvature in dimension 4. And so I want to state an extremality result. And again, this is joint work with Jackson. We put it on the archive this year. So here's the statement. We have a 4 manifold, closed 4 manifold. Let's assume it's simply connected and has positive, or rather non-negative sectional curvature. Okay. If it has non-negative sectional curvature, there's a tau, right? Some tau exists. I need to make an assumption on that tau. So the assumption is that if tau such that R plus tau star is positive semi-definite, if this tau can be chosen either non-positive or non-negative, so it doesn't change sign, then the metric is area-extremal. Okay. And there's a rigidity statement as well, which is, it looks the same as the Semmelmann. If you have this kind of pinching, scalar over 2, bigger than Ricci, bigger than 0, then the metric is area rigid. So to recall, being area-extremal means if you can't increase the scalar curvatures unless you shrink some areas. Area rigid means you can't do that even with a different metric. The metrics have to be the same. Not just the scalar curvatures have to agree, the metrics have to agree. Okay. And it was nice that that you asked me about some examples right before, because I can tell you where this theorem applies. So as a corollary, you can get some area-extremal metrics on some well-known manifolds. So let's begin with CP2. So by the Goethe-Semmelmann result that I discussed, CP2 with the Fubini-Studi metric, of course, is scalar, has positive Ricci curvature, so it is area-rigid. The Goethe-Semmelmann work tells you that in a neighborhood of Fubini-Studi, scalar metrics in that neighborhood are also area-rigid. What we can do is we can take a neighborhood in the space of all Riemannian metrics, not necessarily scalar, and still obtain area-rigid metrics there. So the statement is that on CP2, there is an open neighborhood of the Fubini-Studi metric in the space of all Riemannian metrics, not scalar or anything, consisting of area rigid metrics. Okay. In particular, you can produce metrics with generic holonomy there, right? You could also do a new topological type. So the example that I mentioned a little bit ago, CP2 connected some CP2, this manifold here could not be probed before with the methods that were available, because this guy does not have scalar metrics, so does not admit scalar metrics, nor does it admit metrics with positive semi-definite curvature operator. So you didn't really have any criterion to establish rigidity on it, but you can prove that that it has some area-rigid metrics. So on CP2, connecting CP2, I'll just be very vague on what they are. These, for people who know it, these are the metrics constructed by Cheeger. There exists area-rigid metrics. I'll maybe just point out one thing. Conceptually, these metrics with non-negative sectional curvature built by Cheeger, they look kind of like the pictures I had on the sphere here before. They have some kind of neck region where everything looks like a product. But for the same reason as here, if this neck was anything with positive length, you could play this kind of game of enlarging it, so you wouldn't be able to get rigidity. The metrics that I'm talking about, somehow what happens is that this is infinitesimally thin. There's two pieces and they're glued along just one surface. The sectional curvature is 0 along this surface, but it's just a hypersurface. And so this distance here is this length neck is equal to 0. Those are rigid. You can also do something like this with positive length, and then they are just extremal. But if you want a rigidity statement, you need to be a little bit careful on the construction. But anyways, it can be done. So you can produce such metrics there. And I guess I should justify a little bit why should you believe that these objects, these manifolds have metrics where tau is either non-positive or non-negative. So CP2 is not too hard to explain why. If you look at CP2, the curvature operator is positive semi-definite, but if you add just 1 times Hodge star, this is positive definite. So the constant function 1 does the job for the Fubini-Studi metric. If you perturb the metric a little bit, you can easily see that you can find functions which are still positive and do the job for you. So that's easy to find. On CP2, the picture is a little bit like this. So you have tau that doesn't change sign. That's kind of what I was mentioning before. But perhaps one side comment to illustrate how weak or strong this assumption here is, and that tau doesn't change sign, is that you can show that if the manifold is indefinite, if the manifold has indefinite intersection form, or rather, let me state it in a different way and say if tau can be chosen, non-negative or non-positive, then either the manifold is definite. So by 4-dimensional stuff, this is homeomorphic to the connected sum of some number of CP2s. That's why here the examples are 1 copy of CP2 or 2 copies of CP2, which so far are the only 2 where we know non-negative sectional curvature exists. So either the manifold is definite, so it's a connected sum of CP2s, or it's actually isometric to a product of spheres with the product metric, which is also area rigid by Goethe-Semmelmann. So the assumptions in the theorem actually force it to be applicable only to these spaces. However, another way of looking at this is that it applies everywhere it can in some sense. So if you look at the known examples in dimension 4 of manifolds with non-negative sectional curvature, there's not that many, right? So the list is very short. So we know that S4 admits such metrics, CP2 admits such metrics, CP2 connected some CP2, CP2 connected some CP2 bar, and S2 cross S2, which maybe I should list before these. And that's it. So these are the only manifolds we currently know to have non-negative sectional curvature. Of course, these here have positive sectional curvature, but all of these have non-negative sectional curvature. Conjecturally, this list is complete among simply connected manifolds, right? I'm also assuming simply connected. So conjecturally, this list is complete. And if you ask, well, do they have area-extremal metrics? You see this interesting pattern in which both the manifolds that have positive sectional curvature, they have an open set of area rigid metrics around their canonical metric. So in the round sphere has a positive curvature operator, a neighborhood of it consists of area rigid metrics. On CP2, by the corollary I just mentioned a little bit above, you have such a neighborhood as well. On the manifolds that have non-negative sectional curvature and are not also conjectured not to admit positive sectional curvature, strictly positive. On these manifolds, you have area rigid metrics on all of them as well. So the product metric of spheres is area rigid. CP2 connected some CP2 by the result I just discussed. And CP2 connected some CP2 bar, it actually has scalar metrics with positive Ricci curvature. So the earlier works of Goethe-Semmelmann apply. So it kind of completes the picture among known examples. Everywhere you have positive sectional curvature, you have an open set with area rigid metrics. Everywhere you have non-negative sectional curvature, you have extremal metrics there as well.
Can I ask a question?
Yeah.
So usually when I think of rigidity theorem, I think that there's like some special field, like a killing field or something or parallel field that splits the manifold, something like that. Is there, do these, I mean, I guess I'm a little bit confused because some of these like generic holonomy, you've shown that there are some generic holonomy examples of the rigidity. Can you comment on that? Are there some special fields that on these spaces, or what can you say about can you say a little bit about the rigidity, how you get rigidity? Or is my thinking of, well, you should have some sort of field that splits the manifold?
You will have some spinors that are harmonic and things like that coming up, right? So that's I guess where you're perhaps thinking about. I mean, I'm not completely sure. I understand, but
okay. Well, I'm just thinking like not only harmonic spinors, but sometimes you have like a parallel one, but these spaces I guess don't have such.
No, not really. I mean,
equations. Okay.
Well. Yeah, I mean, I'm not. I can't think of anything relevant actually that I would.
Okay, yeah, I mean, it was maybe too vague to be even a question. But let me also ask: so you also have like theorems where if you have like a non-zero degree map to these spaces, then okay.
Yeah. So okay. So in here the usual games apply. You can, instead of just talking about rigidity and extremality and comparing metric tensors, you can consider maps between, well, they have to be both four-dimensional though. So you have some kind of competitor metric down to M. And so you can allow these topologically modified competitors. You end up needing some condition on the degree of F that is related with the Euler characteristic and signature of these manifolds. So some condition needs to be satisfied. It's trivially satisfied if you're using the identity map. But if you want to allow for these maps, there's some conditions on the degree and Euler characteristic. I could tell you what they are, but yeah, I mean, just some inequality.
Okay.
Yeah.
Okay, it's to make like the index theorem work out, I guess. Or...
To make the index theorem work out, exactly. Yeah.
Okay.
Yeah.
So I have a question now that we're right on this. Yeah. It would seem to me that you could also deal with like S3 cross S1 or like, surfaces that are finitely covered by S3 cross S1. Is that, I mean, because you're just using this for simply connected ones, but do you actually need the simply connected hypothesis?
No, not really. It makes my life a little bit easier, but in general, I would need, let's see, if I want the identity map between the same manifold here, if I again have M, then the condition would be that 1 plus B2 plus minus B1 is positive, I believe. This is what I would need. So it would still not work on well, let me see. So you're asking, you take S3 cross S1 with the product metric, right? It has no negative sectional curvature.
Right.
It has positive definite curvature operator, so tau can be chosen identically 0. But having non-negative curvature operator, it means that it's already area rigid or area extremal, at least by Goethe-Semmelmann, right? So at least in that case, you could just use the earlier results, right?
Okay.
For extremality here.
Okay, thanks. Yeah, I was just trying to figure out what you actually needed and like whether that covered other examples. Yeah, that's a good explanation. Thanks.
Yeah, we thought for a bit about finite quotients of these guys, and anyways, it gets, you can say something, but it feels like this is the more meaningful statement. I mean, whatever we can say on the non-simply connected case, it was not satisfactory enough to convince us that we should state the theorem like that. So, but you can extract some thought. Yeah.
Thanks.
That will also be perhaps evident when I think let's see how we're doing. Yeah. So I might be able to say a few things about the proof, and then you'll see how these things will generalize. But perhaps before doing that, also to connect with the previous talk, I want to discuss some local versions. So versions with boundary. And as was pointed out, you need some kind of condition. If you're having a manifold with boundary, you need some kind of condition on the mean curvature of the boundary here, right? So you need to adjust the definition of area extremality and area rigidity. So let's see a sense in which we can do that. So let's say we have a Riemannian manifold with boundary. Riemannian manifold with boundary is area-extremal in the sense that for the sense that I'll use in the results below, if anytime I have a new competitor metric G prime that has scalar curvature bigger or equal than the original scalar curvature, the area elements, so wedge 2G prime is bigger or equal than wedge 2G. But now I need to add something about the boundaries. So I would like the boundaries to be isometric. I'd like the boundaries to actually, the tensors to be the same along the boundary. So this is a little bit stronger than in some other similar results. And the mean curvatures also compare. So the mean curvature with respect to the prime metric is bigger or equal than the original mean curvature. So if you have a new competitor metric with all these inequalities, then equality must hold on the curvature inequalities. So scalar curvatures are actually the same, and mean curvatures of the boundary are also the same. Okay, so that's area extremality for the purposes below. And just like before, area rigidity, if you get that that under the same set of inequalities, the stronger conclusion that the metric tensors agree. Okay, so I use the exact same conventions as before. So for me, mean curvature is with respect to an inward pointing vector. So if you take a small spherical cap, the mean curvature is positive and points up. And such a thing, such a small spherical cap, is also convex in the case that the second fundamental form is actually strictly positive in this case, right? So with these conventions, we can state the following result. So so this is a local comparison result, which there's also a second one that I'll discuss, which is the analog of what I did before. But I think this somehow takes less to state, and it's kind of interesting in its own sake. So if you take a four manifold with let's say it has positive sectional curvature at a point. So if X is a manifold that has positive sectional curvature at some point, so all planes based at that point are positively curved, but outside of this, anything can happen. Then sufficiently small neighborhoods of that point, sufficiently small convex neighborhoods of this point with all curvatures positive are area-extremal. So you have your manifold, your four manifold, maybe there's some negative curvature somewhere, but there's some places with positive curvature. If you take small neighborhoods of the regions with positive curvature, you can't deform the scalar curvature there to make it bigger, keeping the mean curvature also going up unless you shrink some areas. Okay. Right. So this is actually this statement is actually a special application of the analogous result to the first theorem that I stated. So let me just tell you what that version is. So you have just a manifold with boundary. So actually I can be very lazy since I'm not on a blackboard. I can just take this and copy and paste. I'll tell you how to adapt it. So the version with boundary is the following. So it's no longer closed. It's manifold with boundary. And we need to assume that the second fundamental form of the boundary is positive semi-definite. So it's convex. So I have a four manifold with boundary, positive semi-definite second fundamental form, and non-negative sectional curvature. The rest of the statement is exactly the same. Because it has no negative sectional curvature, there's some tau. If the tau can be chosen non-negative or non-positive, non-positive or non-negative, then the metric is area-extremal. If you have this extra condition, then the metric is area-rigid. Okay. All right. So let's see. I guess I can now say a few things about the proofs of all these results. So I'll discuss the closed case, but you can imagine the adaptations are. I mean that I guess exemplifies well the methods also in the boundary case. So let's do an outline of proof of theorem A, the first one. Okay, so we're going to use spinor methods as well, right? And the idea is to look at spinor bundles with respect to both metrics, the original metric and a competitor metric, and look at twisted Dirac operators that involve both of these metrics, right? So you'll notice that there were no assumptions about the manifold being spin, and that's fine because as usual in this business, we can define spinor bundles with respect to both metrics G and G prime locally, even though there's no global such thing. You can define let's say local spinor bundles with respect to G and G prime. And when you tensor them together, you get something that is actually globally defined. So then SG tensor SG prime, this guy here, because the identity is a spin map, I guess, this is globally defined. And we can look at the Dirac operator on this bundle. So we have a Dirac operator that I'll call depending on G and G prime on sections of this bundle. Actually, I want to split the. I should be putting the prime on the first slot actually here. Let me do prime G. So we take the spinor bundle of G prime and twist it with the spinor bundle of G. So I want to split the spinor bundle of G as spin plus and spin minus, and I'll just use the positive part here to twist. So this is the Dirac operator that I want to look at.
Can you comment on, so usually when you take this tensor product or something like it, you usually get a bundle of differential forms. Is there any relation to just the usual?
Right. So if G and G prime were the same, this would be that's this usual thing, right? That spinor tensor spinor is just the exterior algebra, right? If the metrics were the same.
Even with the plus there, even when you just tensor with the plus part?
No, then you get just parts of it, right? So you have all these splittings of the exterior algebra into even and odd, or even plus, even minus, odd plus, odd minus, right? So you get just part of it. So actually, I'll go into that split in just a second, because we need to specialize to just not the whole thing, just one part of it, right? So this guy here has a plus part and a minus part, and this is with respect to the splitting of SG prime, right? So I'll actually be interested in the index of this operator here, of this guy, right? And I'll tell you what the forms are in just a second. So let's see. If we look at SG prime plus tensor SG plus, which is the domain of this fellow here, it sends this to, it flips the sign on the first. So this is the same, if the metrics were equal, this is the bundle of plus even forms on the complexified exterior algebra. So so even degree forms that when you act by Clifford multiplication with the volume form, it's itself. Okay. So yeah, so we want to look at the index of this operator to show it's non-zero, to get some something we can apply the Bachner formula to, right? So the index of this operator plus. Here's the trick, right? So you can pretend the metrics are the same, even though they're not, because the indices will be the same, right? So it doesn't depend on the metrics, right? So this is the index of and under these identifications, the Dirac operator here is just d plus d star, right? As usual, restricted to the right space. So if you compute this index, this ends up being the dimension of the kernel of d plus d star on even plus forms minus the dimension of the kernel of the other guy up there, which is conjugate to d plus d star restricted to negative odd forms. So if you compute this in terms of Betti numbers on the manifold, this turns out to be 1 plus b plus, so the self-dual part of the second Betti number, minus the first Betti number, which is 0 because I'm assuming it's simply connected, right? And so this thing is positive, right? So you have a section. So I have a harmonic section in the plus plus part. So I have spinor plus tensor spinor plus G, non-zero harmonic section. Well, in the kernel of this guy, right? Okay, so this is where I want to start, and it's important that I went all the way down to this guy, right? To this plus plus part. Just by, you know, if you look at the whole spinor bundle, you'd get just the Euler characteristic, I guess, right? But then you just have some section somewhere. It's important that the section lives in this space, because the condition on the sign of the tau will be meaningful only on this subbundle. Okay, so that's the next part that I want to comment on. So so here's how it shows up. You want to apply the Bachner Lichnerovitz Weizenbach formula. And if we use this together with the fact, so I'm going to combine a few results already just to jump ahead to the conclusions. So if we apply it knowing that wedge 2G prime is bigger or equal than wedge 2G, and knowing that the sectional curvature of G is bigger or equal than 0, what you get is that the Dirac operator squared this is bounded below by the rough Laplacian plus some curvature stuff, and that is 1/4 scalar curvature of G minus scalar curvature of G prime. And there's this T term that depends on the curvature operator of the metric G. So everything would be done if this guy was not there, right? So we need to control the sign of this guy. So let me tell you what this guy is. This T term is such that, well, first of all, it's linear in R. And this T, if you stick in something which is positive semi-definite, you get something positive semi-definite. So if the curvature operator was positive semi-definite, you'd be good. And that's essentially the Goethe-Semmelmann proof. But it has also this interesting property that if you stick in Hodge star, which is the modification that we're using, this doesn't have a sign, but if you restrict to spin plus, tensor spin plus, then it does. So restricted to spin plus, tensor spin plus, this is positive semi-definite. Okay, so the game is you don't know that the curvature operator is positive semi-definite, but you know that the curvature operator plus tau Hodge star is, right? So you know that this fellow is positive semi-definite because you're starting with something that is positive semi-definite, but this is the same thing as tau R plus, or TR plus tau T Hodge star, right? And this has the correct sign if we fix the orientation, right? So we can fix an orientation such that tau is less or equal than 0, because in all this business, if we're flipping the orientation, we're just changing the sign of Hodge star. The curvature operator is the same, right? So I can change orientation and arrange. I don't know if my tau was non-negative or non-positive, whatever it was. Fix the orientation so that it's non-positive. Then from the formula above, I can just conclude that G, Dirac operator GG prime, is bigger or equal than rough Laplacian plus the scalar curvature part. Because this tau R is equal to something positive semi-definite minus this tau times something positive semi-definite, and tau is non-positive, so everything adds up, right? So the whole thing is positive. I can just get rid of it, and now I apply it to the section that we knew from before, right? So the index theory gave us the section C. Let's plug it in. And then integrate, right? So we get that 0 is equal to the square norm of grad C plus 1/4 scalar G minus scalar G prime C squared, or actually bigger or equal than this. And now we're in business, right? Because this was assumed to be non-negative, so they have to be the same. Right, so that's extremality. Okay, so I'm not going to bother you with the rigidity part. It's essentially the same. It's the same arguments from Goethe-Semmelmann. You just need to milk a little bit more the formula here, and use some clever linear algebra. So it ends up being a very nice linear algebra statement. The curious thing about it is that it doesn't work in dimension 2. So the motivating problem that I did in the very beginning with surfaces, I was just dividing both sides, right? And somehow that's the way to do it in surfaces, because the argument that you do for rigidity needs at least 3 linearly independent vectors. And anyways, this is a curious observation on the side, but rather than going into that, maybe I'll just finish. I think I have another couple minutes, perhaps. I'll just add one thing here about the local version. So the proof in the local version follows some recent work of John Lott, and you can imagine how you would adapt all the arguments. Instead of a Tia Singer, we need to use a Tia Patodi Singer. There's some contributions from the boundary that will show up, right? But at this stage in the game, this very last line, the way that it would look on the local version is, well, I can be, again, take advantage of still not using a blackboard. Maybe I'll just copy this part. So you would have some mean curvatures of the boundary showing up as well. So what happens there is that you get this plus 1/2 integral on the boundary of the difference of the mean curvatures. Okay, so when you do the local version, you end up getting rigidity because you have this extra term. The index theory part also changes a little bit. So the index of the appropriate Dirac operator ends up being something like 1/2 Euler characteristic plus signature plus the even Betti numbers of the boundary. So B0 plus B2 of the boundary. Okay, and this is the thing that needs to be positive for me to get a section C to which we apply the earlier argument. And you might look at this and be, well, why is this always positive, right? So this part, if you just look at this part, this is 2 times 1 plus B plus or B2 plus. But then you still have this, and well, actually, this is in the simply connected case, and we're not. I mean, let me maybe erase this because I'm mixing a lot of things up here. This signature is a signature of a manifold with boundary, right? So it's a bit trickier than that. Anyways, the way to get this inequality doesn't go that route. The way to do this actually uses the Stolz theorem, because we have a 4 manifold with boundary with non-negative sectional curvature, right? And the boundary is convex. So the distance function to the boundary is concave. There's a set of maximal distance. You can do the Soll construction, and your manifold is a bundle over the Soll, and you end up being able to prove case by case, depending on the dimension of the Soll, that this inequality always holds. So it's actually a bit of a brute force approach here. So you have a 4 manifold, which is 4 manifold with boundary. It's a disk bundle over its Soll. You just go case by case and you see that this inequality is always true. So you actually don't need to assume anything. It's the topology takes care of itself somehow. The Stolz theorem forces the topological conditions to hold. So you always get a section, non-zero section, to which you can apply the Bochner formula, the Bochner argument to get rigidity. All right. So I think I still have a couple minutes, but I should probably stop here so that we can have more discussion and ask questions and so on. So I'll stop there.
All right, thank you very much. Let's thank Renato.